Hello and thank you for joining us for this latest AMS webinar with TRUMPF Automotive. I'm Nick Holt, Editor of Automotive Manufacturing Solutions. With the increase of hot form parts in car models, Tier 1 suppliers and OEMs are challenged to gain additional flexibility in the production process without giving up efficiency or increasing the cost of their part. Laser technology offers a desired flexibility by taking into account process costs and production capacity. Today we're joined by two of TRUMPF's Global Key Account Managers, Michael Fritz and Johannes Berg. Together they'll be shining a spotlight on the latest laser applications in hot forming, discussing how this leads to shorter cycle times, more efficient and effective usage, and raised productivity in the production process. Together they bring a wealth of experience in production technologies and in particular laser systems. Now, before I pass over to them, I'd like to remind all of you in attendance to draft some questions for TRUMPF, which they will be pleased to answer in the Q&A session following the presentation. Please ask your questions by typing them into the box on the lower right-hand side of your screen. If you should experience any technical issues during this session, please also type these into the Q&A box, and our team will do their best to sort these out for you. We hope you'll find this webinar stimulating and informative. And now I'll hand over to Johannes to begin the presentation.
Hello everybody, thank you for joining our presentation. Before I start, I would like to make a short introduction of our company. So we are a high-tech company for laser and machine tool technology, and our main activities is making industrial lasers and machine tools, which mainly are related to the laser business as well. With approximately 10,000 employees, we are represented in all world markets close to our customers. So we consider ourselves the world leader in laser technology. That's a fancy word, but it's actually true that we are the biggest machine tool manufacturer with laser in the world. In terms of diode laser power, we are the biggest producer, and we are the only company with this high product portfolio with, for example, micro lasers, pulsed lasers, marking lasers, high power lasers, low power lasers, and so on. And also we are the only manufacturer of, which will be seen in the presentation, for 3D cutting machines, and we are the only manufacturer doing the same machine and laser source at the same time. We also have some other business fields which is not on that slide. It's we are in medicine technology and hand tools and so on, but we just focused here on our main activities. Going to the automotive sector, which will touch our hot forming topic today, we have different laser applications. And I would like to outline the majority of these applications which are our customer using in their applications. Our lasers mainly for cutting, 2D, 3D, welding, remote welding, laser bracing, which is a very common application, ablation, which we will talk today in this presentation, laser hardening, softening, marking and engraving, cleaning of edges, metal depositioning, and of course drilling in injectors and so on. So going to the hot forming topic, what is the main motivations of our customers, of the OEMs, to use hot forming parts? I think I don't have to introduce and explain hot forming, but the main motivations for it, it's to reduce weight, and that means reduce fuel consumption in the cars. And the second motivation, of course, is increase the safety of the passengers in the cars. So on the right-hand side, we see a state-of-the-art car model, and in colored we can see hot forming parts used in a body-in-white frame. So their customers, they use around 20 to 30% of their car body using already hot form parts. So it's really a mega trend, and state-of-the-art cars are increasing using this kind of parts in their models. I always like to show this slide because it tells a lot, and you can see on the upper side the process chain of hot forming, which is typically starting from coils. The parts are blanked, typically in presses. It's a mechanical blanking. For preparation, many times there is a edge preparations. Then in many parts they use patchwork or tailor welded blank parts because of different material thicknesses. And then the flat platen blank goes through the oven, is heated to the process heat. The parts are formed in the press, and later on we have our main activity, the laser cutting, and afterwards there's a new trend for part softening, that they need to soft up in defined areas of the part for example crash reasons. And afterwards, after the process chain, basically there are steps like laser welding, laser marking in the assembly of the car body. So in the lower part of this process chain, I would just like to outline our activities or the activities of our customer with our laser sources. So for example, for flexible lines, there are 2D cutting machines used instead of very static presses. So this gives flexibility in changing over between one and another part. It's just a programming issue. And there is of course also automated solutions. So it's not only the cutting machine, it's also the loading and the unloading of the parts and the handling of the parts. Later we have in the tailor welded blank business, there are our disc lasers and CO2 laser used. Nowadays we will talk this later on, the preparation of this welding edges with our micro lasers, and tools are wearing out, so tools have to be refurbished with laser metal depositing process. So this is a very interesting application to refurbish the tools. It's a wear part, mechanical part. Then of course our 3D laser cutting, and afterwards softening of parts could be done with our induction heating systems or with laser on surface, and of course laser welding, laser brazing, and remote welding in these processes. So but today we will focus on ablation with our micro lasers, and we will focus on the 3D laser cutting. Otherwise, if we would explain all this application, we would not finish probably within this hour we have available for AMS. So I want to outline one trend which we can see in hot forming, that OEMs are using tailored probered hot forming parts. That means they want to increase more the weight in the car. That means they want to bring the fuel consumption down, and consequently they have to reduce the weight. And that means they use only the thickness of the material where they need it, and in other areas they use a thinner material, which can be done by roll forming, or one of these applications is tailor welded blanks. Tailor welded blanks to do with aluminum silicium coated steel is quite a challenge, because the aluminum silicium coating in the welding seam area is not doing really not helping. So what they have to do, they have to remove the aluminum silicium coating on the steel to be able to weld or to get a good and strength welding seam. So this layer is about 10 to 20 micron thick, and we can see here on that photo, this is the thickness of that layer, and this is a typical part, different thicknesses, and they have to be welded in 2D as a tailor welded blank, and maybe or steels with different different properties of hardness for crash properties. So the process requirements we got from our customers is to remove 10 to 20 or even 30 micron of this aluminum silicium coating, and only along the welding edge of the blank. That means you cannot remove too much because of corrosion issues, and also the process must be very stable, so it must be adjustable to have this thickness, to take off the thickness in different height. They don't want to change the property of the base material. That means we cannot bring in heat in the material. The removable width is typically 1 to 2 millimeter thickness, depending of the welding seam thickness and the laser source and the thickness of the material they weld. Typically it's 1 to 2 millimeters at the edge. Also a requirement could be the simultaneous removal of two sides of the blank. That means you have to take off the layer on the upper side and then the bottom side, just to make sure that no aluminum is going into the welding seam. A typical welding speed in the tailored welded blanks machines is around 6 to 8 meters per minute, and so the resulting linear removal speed should be around 12 meters. That means we have to take off on the upper and on the top side and the bottom side. So in overall to 12 meters to not create a bottleneck in the process. So what we did, we used different setups. We made many tests in our laboratory here, and we just wanted to understand this process to be able to transmit it to our customers and to make a good technical and industrial application out of it. So we started at the scratch with a typically round fiber, and also a square fiber, a rectangular fiber, and we created with our optical setup in our head a line focus. So we really tried many parameters, but basically we used these 4 different optical setups. So on the left hand side we see just symbolically the fibers. On the right hand side we see an ablation spot, and you, for example, to get to a straight line going in that direction, we really have to make a lot of pulses, overlapping pulses, to remove the layer, and the same we do here, and we really played with these different overlappings of these layers. For the laser source, we used our nanosecond laser from the True Micro series, which is a very high productive laser source with high laser quality. That means we can use small fiber with small diameters, which helps us in terms of optical arrangement in the optic. So we can really we could really play in different optical arrangements. And very interesting of that laser is it has a very high pulse energy power with a high repetition rate, very stable in the pulse, which helps, of course, in that removal of the part of this very thin layers. And we can go to very high frequencies, which we'll explain now. So very important in this kind of applications. I prepared 2 small videos just to see how is that working. First, we will start with a high-speed camera where we can see in very accurate films, very slow motion, to see that how every single pulse is on that surface and shooting up this aluminum silicium layer. I will just step out and go to the videos. Now we can see 1 millimeter width. So this is 1 millimeter, and these are the single pulses. We're blowing compressed air from the right side, going in the direction of the removing. And below is the clean high-strength steel. So if this would be on an edge, we could now weld this part without having the aluminum in the layer. Now in real time, this looks like, here in this video, this is in our lab on a short high-strength steel plank. So real time is 28 meters per minute, which is really a little revolution in this application, I would say. So let's go back to the presentation. So we did these different trials with these different beam shapes, like I explained, round, square, rectangular, and so on, and the different overlaps. So what is very interesting is if we use a square spot, we go in that direction, for example, with the ablation, we can only use about 25% of the heat conduction for the ablation. That means the rest is just losing to the side edges of the spot. And we did the same with a rectangle spot and with a line spot. And it was very interesting to see that we had a very high possibility and power to go in that direction. But what we do, we use the same energy, but on a smaller surface. That means if you do that, you also have to do overlaps, and you are bringing much more energy per square millimeter surface. And to not slow down the process, because you have a much smaller surface, you have to increase frequency. And it was interesting that our laser is the only one who can really do that job. So here on that comparison sheet, we had we did many trials. I just want to show it in this graph. And the result with that line laser was outstanding. So we did this optical setup with the line shape. We had very good parameters in around 17 meters per minute of ablation rate. And here we can see a little photo of an electron microscope picture, how clean the surface gets with the optimized parameter set. So the summary in facts, of course it's a thermal process, but the nanosecond pulse is so short that it's almost a cold ablation. it's very efficient because we can meet the requirements from our customers. We're not creating a bottleneck compared to the welding, and the quality and the speed and the residue of the aluminum is very nice for industrial application, and it allows to adjust it very nice, and to remove it at 100% or to adjust it to a certain percentage if somebody wants to have an aluminum short layer on top. So we are getting now to the laser cutting part of our hot forming application presentation. I would like to hand over to my colleague Michael Fritz. Thank you very much.
So hello everybody, this is now Michael Fritz, and I will be talking about the other topic in the presentation, the cutting of the hot stamping parts. Good. I also want to point out some trends that we see in the industry, one of which is that we see a lot of, or a few large parts coming from our customers. That means these are complete door rings, side panels, body sides. Those parts typically require more laser cutting, so they have quite a high complexity. They also require longer cycle times on the machine, and of course also a very large work envelope of the machine to be able to position them in the work envelope and to do the cutting process on them. The other trend that we see, it's going pretty much into the other directions. We see parts with pre-developed lengths. That means a lot of the contour of the parts is already pre-trimmed in the blanking press. Another trend that we also see is the cutting in the die or hot cutting process, which also reduces the content of laser cutting. That means and with those parts we see a pretty short cycle time, and cycle times coming down to in the range of 20 seconds to 30 seconds. So why do we do laser cutting instead of the conventional hard trimming press or trimming in the die? Because what we saw, there's an extremely high wear of the tooling. So a lot of cost involved to repair the tools, to keep them running. Downtime, there's pretty high forces required. That means big presses, which also cost a lot of money. And also the hydrogen embrittlement when mechanically cutting edges of already hot stamped components. With the laser on the other side, we don't have any wear on the tooling, we don't have deformation on the part, and we can also have accessibility with our laser heads into very complex contours and very complex shapes. The two typical laser processes that are used for these materials is nitrogen cutting as a cutting gas, but as a newer trend, or since a few years, I think most of our customers, they also switched over to compressed air cutting, just because of the savings in cost of processing cost. The cut speed and the cut quality is pretty much the same. The difference is that you have a shiny edge with nitrogen and you have a little bit of a discoloration with air. So also another thing, why do we use 5-axis machines? Well, we see that there is a need for very high dynamics motion. So a 5-axis machine is pretty much a Cartesian coordinate system where we have very stiff and rigid axis, so we can follow the program path very accurately. So we don't need to compensate for any slack in the axis. Make a program, we can put the part on the machine and then cut it right away with maybe just a few adjustments. Also, if there is adjustments necessary in the process, which is always the case, that holes or contours need to be shifted and moved, this can also be done very easily on the machine. We have, of course, the laser cable thoroughly integrated into the machine. We have a fairly large work envelope, and we have a very high installation base of those machines. I don't have the number right on top of my head, but it goes into the hundreds, of course. So as a result out of that, we have a very high output, and of course, and that's what really comes down, everything comes down to it, we can achieve a very low cost per part. As a further introduction, I want to show the machine also in a video real briefly, so I have to exit the screen. I think that is for a better connection. So that's the product video. What you see here, with the TruLaserCell 8030, we have greatly reduced the footprint of the overall installation. We have a safety and loading area in front of the machine that allows accessibility to the loading position from 3 sides, which makes material logistics very easy to handle. The rotation table puts the part into the work envelope where we do the cutting. We have features which I later will explain a little bit more in depth, which is the observe line. It's a slug detection. And of course, what you can hopefully see well in your screen presentation, that the very high agility of the machine and also the changeover time from part to part that is shown here. So from turning the laser off and putting the head away to a safe position, putting a new part into the workstation, approach the part again, ignite the beam. That's pretty much the time from part to part. It takes right about 5 seconds here. If we only look at the rotation time, it's a little bit over 2 seconds, roughly 2.5 seconds. So this should have served as an introduction of the equipment that we have especially developed for this kind of an application, because we saw this market is really growing a lot, and we also saw the need to have a special machine tailored for this kind of an application. Coming back to a few topics here, again having a screenshot of the loading area where you can see how you can place your bins and crates around the machine to have a very good machine logistics or part logistics, get parts in and out. When I come to a function of the machine, which is called fast line, this is a function that allows the piercing on the fly. At the end, what it does, it reduces the cycle time. When you look at the left picture here, that's the normal sequence of piercing. So the laser head would come to a pierced position. This is a hole cut into the sheet. Then you ignite the laser, you start cutting the hole, and you go up and go to the next hole. With our piercing on the fly or fast line cell, while we approach the hole, we already ignite the beam and ignite also the distance control. So we have already the very high energy density on the part when we come to the piercing position. That means we can start to cut this hole much faster. What we save here is roughly 200 to 250 milliseconds for each time that we do this piercing. So now if you count typical part, maybe 20 holes, well, you can do the math. Another very unique feature that we have built into the machine is observe line. This is what we use to make to deliver better quality or to make quality control of this machine. And how this function works, if you have paid attention to the video, it was just a very short sequence. But what is done is the laser emits a very short pulse after we have cut a geometry hole. This laser pulse of course goes through the cutting optic to the position where a hole is supposed to be. Typically, the slug is fallen out of this hole, and nothing will happen. But just in case a slug is getting stuck into a hole, which can always happen, then some of the light is being reflected through the fiber cable back to the resonator, where we have mounted a sensor that you see here indicated a little bit in blue. This sensor will give an error message or error signal, and the part can be treated accordingly and be taken out of the process. So the same thing we can also do, of course, with our distance control, which is a capacitive sensing system. But it turned out that this optical system is way faster compared to capacitive fields, and it also can detect cutouts and holes which are much smaller. So we can achieve a very high process safety in this case. Another important feature here to increase the productivity, mentioned that in the presentation, in the movie, it's the rotation time of our table and the total part changeover time. So now if you put this into relation to typical cycle times that you see in those hot stamping components, which is down below this chart here, typical times range maybe from 30 to 60 seconds. You can see the advantage in productivity just by increasing this rotation time from 7.5 seconds to 5 seconds. And the benchmark 7.5 is because these are typically available rotary tables that we find in the industry, and also previous generations of our machines had this 7.5 seconds changeover time. And we really wanted to set the benchmark, so we have looked into a lot of details of the machine to improve it and to make it more productive. Another thing that we have done since about many years, down here you see the years 2005 to 2011. That's when we really started to cut those components in very high volumes. Back then we had a chance to get this part here. It's still our benchmark part. It's a B-pillar, actually of the Passat B6, and the cutting length is a little bit over 6 meters, and it has numerous holes in it. With our machine generation from back in 2005, it took us 120 seconds for completely processing the part. So with introducing new generations of machines, new laser technologies, packages that increased the dynamics of the machine, we brought this cycle time down to nowadays about 47 seconds. So really shortened the cycle time a lot. This graph is showing the same thing over again up to this point. Now bringing down the cycle time of the parts, which is one due to the increased dynamics of the machine, but also due to the pre-development of blanks and lower laser cutting content compared to previous years that we have seen in industry. That means for the operator it's really very difficult and tough to keep up and with the machine throughput. So we see that operators are getting or being a bottleneck right when we get to a cycle time of around 40-45 seconds. That's when really an operator has difficulties to keep up with the machine. So therefore, in addition to the loading strategy of loading the machine manually, which is mostly used in the industry, of course there's also automation available now. The machine offers an interface for all the robots pretty much. And we also have developed a solution to load the machine automatically. Now the sequence of automated loading looks a little bit like this one here. This is the situation that we find at a lot of our customers. Parts are delivered in boxes or crates or bundles, and within those crates sometimes they're stacked, they're laying down, there's cardboards in between them. So it's pretty much an undefined position and location. So this is really difficult for automation, of course. For automation, you need to at least to have the parts presented to the robot with the accuracy of about 50 millimeters. This can be achieved stacking the parts into a rack. In many plants there's already these kinds of racks available, and parts are handled in the racks. So, but accuracy of plus minus 50 millimeters is still not good enough to locate the part accurately, to grip it with the gripper hand of the robot and to put it into the machine. So we need to achieve here a better and a higher accuracy. So therefore our engineers have developed a sensor system which is made out of laser line sensors which can detect the part position, the part location, and also adjust the position of the robot gripper. On this slide you see here this laser line is projected over the contour of the part at defined positions. If you see in the middle section, in the middle picture here, there's 1, 2 and another one on the other side here. There's 3 positions on the part which are measured with this sensor. And with the data that we gather here, we do the correction of the robot gripper, or the gripper arm of the robot. Of course, the robot will do the checking again to make sure that it's in the right position, then taking the part and loading this part into the machine, and doing this with an accuracy of about 1 millimeter. So if we achieve this accuracy of about 1 millimeter, we can make sure that the part in the fixture is located in a good, in an accurate position, and can be processed from there on within the machine. Good. So, better than explaining everything is, of course, showing a movie on here. I think I have to do this one. So this is now the cell that we have equipped with a robotic gripper system. So when the robot goes to the part, you can, for a short moment, you can see the red lines on 3 positions. The robot is adjusting its position, getting the part, and load it on the fixture. So of course, the robot loads the part on the fixture very accurately every time it does it. The difference, what we see with an operator, is operators put the part roughly into position, and later on give the part a push, and what we see here is that the locators of the fixtures are wearing off a lot quicker. At the same time, the machine in the enclosure is doing the processing while the robot is loading new parts again. So in case there would be an erroneous part coming out of the machine, detected by observe line, of course the robot can also take care and get this part out of the sequence of the processing. Okay. So I will also summarize here the advantages that we see using a robot for loading the machine. We call our solution LiftMaster Robot. What we see here, of course, what the advantages are is we have less operators involved in the complete process. We can share one operator over many machines because the robot is really taking care of the loading and unloading. So we can lower the hourly rate for the machine. What was also seen having this in production it's a very high continuity in the process. That means the robot puts the parts in very steadily. It doesn't make any breaks or stoppages, and the signal exchanges are very quickly happening, so there is reduced idle time. We also see the accuracy of putting the part on the fixture, which helps to reduce the wear on the fixture. Anytime when you give the part a push, you have pretty much abrasion happening and wearing off the pins where the part is located on. And we can also take care of bad parts that are detected by observed line and take them out of the process. So all of this, of course, it results in the reduction of cost per part, which I think is the goal of everybody doing this kind of a process. And we can also deliver a higher quality of the part because the part is positioned in the fixture very accurately anytime we load and unload a part. So this brings me to the end of this presentation. And I think we'll switch now back to Nick because he has also some task for you doing a little poll for us, please.
Thank you to Michael and Johannes there for a very, very interesting presentation. Before we move on to the Q&A session, we have 3 questions that we would like to ask you, the audience. They'll be appearing on screen. And I hope you will answer these and feedback your replies. Our first question is, where do you see the potential for laser technology in your production process? And you'll see there's a multiple choice answer there, so if you just tick the appropriate box. Okay, and our second question in which part of the process chain are you interested? And again, multiple choice question here, so tick the appropriate answer. Thank you. And our final question is, are you planning to invest in laser technology in the future? Thank you very much for your feedback there. Well, we can move on to the question and answer session, and we've had a number of questions presented to us. I'll ask each of the questions, and Michael or Johannes will provide the answers, hopefully. First question, gentlemen, is why is laser cutting more cost efficient than mechanical cutting? Can you give us some examples and some explanation there, please?
Okay, this is Michael. I think I will answer this question. I think I had a slide in my presentation about this. What we really saw at the beginning of hot stamping, or actually when it really took off as a big trend, let's put it that way, in the early 2000s and in the middle of 2000, I think a lot of parts were still mechanically trimmed and cut. but the companies doing the processing, they saw a lot of issues with breaking down tools, because the material after forming it is very hard. So steel on steel was causing a lot of wear on the tooling, and of course wear and breaking of tools requires cost. So it turned out that laser processing was here more cost effective or cost efficient, how you call it. Next question, please.
Next question. Our question here is, what cutting velocities can be achieved with laser technology?
Okay, this is Michael Fritz again. I'll also take this question. I mean, it really depends on the part geometry. It depends on the material thicknesses. If we cut thin material, thin gauge material, we achieve speeds of more than 40 meters per minute. But this is not really too relevant, I think. I mean, I don't have all the numbers in my head, of course. But what we encourage our customers to do, really to make cycle time studies for each individual part, because the complete process, it depends also on the complexity of the part, how much reorientation needs to be done with the machine, with the laser head, dynamics of the machine, and things like that. So, I mean, all the numbers that you read on paper as far as speeds, laser power, and things like that, I don't want to say they're irrelevant, but really what counts is the cycle time at the end of the day. How quick do you get the part out of the machine? The next one in. Next question.
Okay, thank you for that. This is regarding a specific piece of equipment. Regarding the 8030, why do you say this is currently the most dynamic 3D laser cutting machine on the market?
Okay, I will switch over to Johannes, so I have to pass over the microphone to him. 1 second, please.
Okay, this is Johannes. I will take that question. Well, that's an easy answer actually, because we've seen it in the presentations. The high accelerations of the machines up to 10 meters per square second. Then, of course, the features for the piercing, the fast line was it named, and the slack detection, and of course the shortened idle times for the rotary table, with this 3 seconds or less than 3 seconds, and the positioning of the heads. So, yeah. Next question, please.
Thank you. Do you think that the automation of laser cutting machines, sort of robotized loading and unloading of parts, is going to be a strong trend in the hot forming process?
Oh, that's a nice question for Michael, I would say.
Okay, and this is Michael back now. Yeah, of course, before we started to design the robotized loading of the machine, of course, we have made thoughts about, are we going to be able to sell it in the market? We have done some studies. We went to a lot of customers asking them about their opinion too. Now we have done the sell, and what we really see is that there is still a lot of the machines being manually loaded that go out into industry that we sell. We clearly see the advantages of the robotized loading, and my personal opinion is that when the cycle times are coming further down, when we see more parts with cycle times at 30 seconds or 40 seconds and below, that's when we're also going to see more and more of the robotized loading. And the trends that we see is that there are still very complex parts that require a lot of laser cutting, so it will have its place, but maybe the majority will still be manual-driven systems over the next years.
Thank you. And sort of staying on the subject of robotizing, do you think robots will replace Cartesian 3D laser cutting machines like the 8030 or others in this application?
Well, I will take that question. This is Johannes again. We do see some potential for robot cutting in the market, but definitely I would say not, because of the high machine dynamics in combination with the positioning and path accuracy compared to a robot system. Our 5-axis machines are outstanding. Also, we have no need for axis compensations of the in-C path, which is programmed. And I think an important argument also is that we have that integrated light cable, which in a robot system you have to take that fiber cable up to the head, and it's a very tough to that light cable, so we have no mechanical wear. And overall, I would say the working envelope, so that means the working range of our machine is higher than from a robot, so you would need a big robot or 2 robots within in one cell to do the same task. But at the end, maybe you can see there's a higher initial investment for a 5-axis machine, but because of that higher output with all the arguments we have seen in the presentations, it's proven from our customers it's a much lower cost per part. So that's we see, like, yeah, to answer that question completely, I would say. Next question, please.
Next question. We have a question here. Do you see that developed blanks or the hot cutting process will possibly replace phasing?
Okay, so this is Michael again. I take this question. I think not too long ago with a presentation I had the same or similar question. Well, actually we hope not. Of course we are competing against those technologies. We see a lot of more and more pre-development in those blanks. However, my belief is that there's also a limitation with pre-developing. More complex parts, parts with high accuracy requirements are typically difficult to manufacture in a way that the pre-development can be used. And the hot cutting, I have also mentioned that in my presentation a little bit, which is the cutting in the die while the part is formed or shortly after the part is formed. I also see that there is quite some limitation on that as well. So to answer the question, I see the laser technology being around in this application for more time, I guess, I hope. Next question.
Next question is regarding tailor welded blanks. Do you think these parts will increase in hot forming applications?
Yeah, what we see is, this is Michael again, what we see is also the trend to more tailored properties, different thicknesses, different materials welded together. And there are certainly other technologies out there, which is the tailor rolling, which is the patchwork welding. So there's different ways to achieve properties, or in the cooling and heating process you can also put properties into the part. But I think it's a cost-driven question, and as long as tailor welded blanks can compete in cost-wise with those other technologies, it will certainly be around. So I think it will increase because we will see more tailored properties in the components, and that's why it will keep its share but overall increase. That's my belief. Next question, please.
Another question here is, what is special about the combination of the true micro laser and the line focus optic?
Okay, that was Johannes' topic, so I switch back to him.
Okay, this is Johannes again. Well, speaking of the spot, I would say the line focus, it's a very special shape, what gives us an ideal flow of the heat, but at the same time you have a very high density of the power on the surface. That means you have to increase very high your frequency, your working frequency. And well, the special about is that we see it's the only laser on the market who is able to work in this high frequencies to do this ablation work. And on the other hand, from the laser source, beside the high frequency, we have a very high pulse stability, which is necessary to do this ablation of this thin layer, and to do it in a way which is repeatably and constant. Next question, please.
Thank you. Do you think that tailored blanks will be replaced by tailored tempering or tailor rolling?
No, I don't think so. It's one of these manners to do tailor properties, but tailor blanks compared to roll forming or tailor tempering, I see it as a very flexible application. So I would say no, but well, I'm not the one who decides. Next question, please.
Next question. It goes away slightly from the hot forming topic that was the original starting point, but regarding laser cutting technology, could you discuss some applications for plastics and composites in automotive construction?
To cut these parts, or sorry?
Yeah, I think it's to cut. I think it's cutting these parts. What applications could laser technology offer in the use of plastics and composites in vehicle construction? I'm assuming it would be cutting.
Well, all of them, I would say. That the only thing to cut plastics, these are materials with completely different properties. So we would have to look on the type of laser with the wavelengths. Well, I would say it's a CO2 lasers. What we have in this presentation, we're talking about solid state lasers, so it's a different wavelengths. And the machine would have completely different features. So usually plastic parts are handled in a different way. The cutting process is done with capacitive sensors to keep the cutting path stable. On a plastic part you can do it, so you would have to design different kind of machines. But of course from the laser side this is already done, and it's completely factible.
And we've got one final question. You mentioned at the beginning of the presentation that to change, to retask the cutting system for another job, it was a case of switching over the programs. Do you have any sort of time figures for changing over the program, or does that depend on the application or the part that's being cut?
So there are certainly two different ways, and I don't know if I got the question completely right. If we have a program running on the machine, a part is sitting on the machine, also already programmed, and it's just switch back from one program part to another program part. It's pretty much taking the fixture away from the machine and put a new fixture on and activate the program again. Let's say 10-15 minutes to do that. If you set up a completely new part, this is typically done with offline programming. Offline programming means you have the fixture loaded in your offline program system as a CAD model. The same with the part. You do the programming offline. Later on you go onto the machine and connect the fixture to the machine. You load the program into the machine, and then you do, it's not really a teaching mode, but let's say you run it very smoothly and carefully the first time, of course, because you want to avoid any kind of a collision. But putting it onto the machine, getting it run off, it depends a little bit on the logistics of the plant where you use it. Typically parts need to be verified in checking fixtures or with CMM measuring equipment. So it can take a few hours, but if we only look at the programming and get the part cut and running without doing major adjustments, it can be done in a few hours for a new part.
Thank you for that. That's the last of our technical questions. We've had a number of questions regarding access to the presentation. The presentation will be available on the AMS website from tomorrow. So that finishes our presentation for today. Thank you very much for joining us, and thank you to Johannes and Michael for their really interesting session on laser applications and hot forming. The webinar, as I mentioned, will be uploaded to our archive, so you or any of your colleagues who have not been able to listen today will be able to access it. And you can access all our previous webinars via the webinar tab on the AMS homepage. Thanks again for joining us, and we hope you'll join us again for our next webinar. Thank you.